Okay, Module 17D, we really want to start looking at being able to identify pretty quickly if a system is acidic, basic, or neutral. You need to be able to recognize that small, highly charged metal cations are acidic. And I will go through the process and I will discuss why, but students have a really hard time seeing it. So I need you to really try to envision the particles themselves and envision what's happening in solution so that you can also describe this process. You then also need to be able to describe or be able to predict whether a solution of a particular salt will be acidic, basic, or neutral. And within this, you should be able to eventually be able to determine the pH of these small, highly charged metal cations, as well as any solution that's acidic, basic, or neutral. So what do I mean by small, highly charged cation? Well, first they have to be what we call hydrated. A hydrated cation is like here, this is an aluminum atom in the center. Let me turn it to color so you can actually see. This is aluminum in the center, okay? And it coordinates to 6 water molecules. Hydrated means that it's surrounded by waters. It's got all its waters around it. And it forms from small, highly charged metal cations, and these cations are acidic. Again, they're small, they're highly charged. What do I mean by that? Well, by small, if we go across the periodic table, size increases across and up the table, right? So the closer we are, as we go across, it gets smaller. So upper right metals, on the periodic table. Now, that means metals, not the upper right of the table, the upper right portion of the metals themselves. Remember, the upper right part of the table is actually your non-metals. But this, in highly charged, +2, +3, or +4 cations. The reason that small matters is charge delocalization. And for some examples, Fe2+, Fe3+, CO2+, CO4+, Ni2+, Cu2+, Zinc2+, Aluminum 3+. Cations that are hydrated, meaning surrounded by water, in aqueous solution, again, aqueous means water-based, the solvent water molecules act as Lewis bases. There's a high charge density on the metal cation. So this metal in the center has a high charge to it, right? It's highly positive. It's coordinated 6 waters to it. So we see aluminum with 6 water molecules. It keeps its charge though because those water molecules are neutral. Another water molecule comes along and it sees that this is highly coordinated. This aluminum is so positive that the oxygens are just like completely attracted to this aluminum. They're just, strong ion dipole force here. Very strong ion dipole force. It's so strong, in fact, that the aluminum doesn't always notice when one of these water molecules will come along and it will just pluck away one of its hydrogens. And it will leave as H3O+, leaving behind aluminum with 5 complete waters and 1 hydroxide. So that, again, the aluminum in the center here is so highly charged, so polarized, that the oxygens are all oriented to it. It's 6 water molecules oriented. Why 6? Think about spatially around the molecule itself. We can fit about 6. Top, bottom, side, front, back. We can fit 6 water molecules around there. Another water molecule in there, those oxygens though are very, very attracted to that aluminum. Not only is water polar itself, remember water molecules polar themselves, right? It's pulling a lot of electron density this way, giving these a partial negative charge and these a partial positive charge. But the oxygen is even more attracted to that positive charge than aluminum, meaning this is completely being ignored and has a partial positive charge. So another water molecule comes along and it's like, hey, you're negative, I'm positive, why don't we hang out together? And it steals this proton. Off leaves my hydronium and leaves behind a hydroxide ion. So high charge density on the metal cation polarizes those electron clouds of the water ligand. Ligand is just something that coordinates to that metal complex. It weakens that OH bond. The proton here is removed from a solvent water molecule, forming hydronium ion, which increases the H plus concentration in solution and causes the overall solution to become acidic. So, let's work a few examples on how this actually looks. These are flipped in my notes. This compound, how could I actually write this out? So, let's first look at, I'm going to write out this zinc one, and then I'm going to erase it so I have space. But if I looked at this zinc, hydrated zinc complex, and it's got a Ka value of 1 times 10 negative 9th. The previous example, which was actually pictured on the previous slide, let me go back. This one is the example in the notes that says this, and this has a Ka value of 1.4 times 10 negative 5th. This is what's actually happening. This is the reaction. So we would write out AlH2O 6, 3 plus, because it's coordinating 6 waters always. Okay, these metal cations are going to coordinate 6 waters. That is a fixed value. Aluminum has a 3 plus charge, and the waters are neutral, so it stays aluminum, H2O6, 3 plus. It's aqueous, it reacts with water. It's forming equilibrium. When it reacts with water, one of those water molecules loses a proton. So now I only have 5 intact water molecules and 1 hydroxide molecule. I've lost 1 proton, but it's left behind its electrons, which means that the charge goes down by 1 and a hydronium leaves. Now let's work that same exact example, or same type of example, with zinc instead. Zinc, hydrated zinc here. I've got zinc, H2O, 6, 2 plus. This is aqueous, reacts with water, forms an equilibrium. Now again, what's happening here is that this zinc is polarizing that bond between the oxygen and hydrogen so strongly that a different water molecule can come along and easily pluck away that proton from one of those waters, leaving behind zinc with only 5 water ligands and a hydroxide ion. But when it does that, it's going to leave a +1 charge instead of +2, and then H3O plus. So the example here asks me, what is the pH of a 0.1 molar AlCl3 solution? I'm going to erase this, and I'm going to give us more space to work. So the first thing I need to think about here is, what is AlCl3 in solution? How does that actually behave? And I need you guys to recognize that too. I need you to recognize that AlCl3 is going to dissociate 100% in solution, forming Al3 plus ions and 3 moles of chloride ions. Now, chloride ions, spectator, because they come from HCl, a strong acid. But Al3 plus, small, highly charged cation. That's going to form an acidic solution. I also see here Ka value that highly suggests that it's going to form an acidic solution. So then the aluminum, 3 plus, reacts with 6 water molecules to form the coordinated complex AlH2O 6, 3 plus. That complex then reacts with water to form an equilibrium with AlH2O 5, OH 2 plus, aqueous, and H3O plus. Oops, erased a little too far. Now this is my equilibrium, and I'm going to set up my ice chart. Originally, I had a 0.1 molar AlCl3 solution. Because it's a strong electrolyte, that means I had a 0.1 molar Al3 plus and 0.1 molar C minus, or actually that would be technically 0.3 molar because there's 3 chloride ions. But it's spectator, so I'm not worried about it. That Al3 plus reacted with the waters and kept its 0.1 molar solution concentration when it formed its complex. So this is also 0.1 molar. Water doesn't matter. We don't have any AlH2O5 OH2 plus present to start, and we assume that our hydronium concentration is small enough that it won't affect our solution initially. Minus x, and equilibrium 0.10, x, and x. Now I set up my K expression. K is going to be equal to the concentration of Al, H2O5, OH2 plus, times H3O plus divided by Al H2O6 3 plus. Now because I've got this H3O plus in my numerator, I know I need Ka, which is nice because that's what they gave me, 1.4 times 10 to the minus 5th. Go ahead and sub in what we know. We know this is equal to x squared over 0.10. You're going to solve for x, and we find x to be equal to 1.2 times 10 to the minus 3. But again, remember that equals my hydronium concentration, right? Now I can find my pH of my solution, and I find the pH here to be 2.93. So as predicted, small metal cation, acidic solution. You do need to be able to determine whether an acid is acidic, basic, or neutral based on its components. So this is really looking at how do you split these up and what will they form. If I split up NH4ClO4, so split them up, pretend you're naming them, right? Split them up. What does this mean? This gives me NH4 plus, which is ammonium, which is a conjugate acid of ammonia. Ammonia is a weak base, so this is going to contribute to be acidic. ClO4 minus perchlorate is the conjugate base of HClO4, perchloric acid, which is a strong acid, so this is a spectator. Overall, this will be acidic. What about KCN? Split this up, I get K plus, potassium ion, conjugate acid of KOH, which is a strong base. So this is a spectator. I also get CN minus, cyanide ion, which is the conjugate base of hydrocyanic acid, which is a weak acid, so this will be basic. This will behave as a base in solution. FeBr3. It's going to give me Fe3 plus and 3 moles of Br minus. Fe3 plus, small, highly charged metal cation. It's going to form that complex with water and form an acidic solution. Br minus, conjugate base of HBr, so a spectator. But overall, this will be acidic. K3PO4. 3 moles of K+. We've just discussed K+. We know this is a spectator. PO4 3-. This is the conjugate base, or one of. Technically the conjugate base of HPO4-, which can also be from H2PO4-, that should be 2-, H2PO4-, and H3PO4. But either way, eventually leading back to phosphoric acid, which is a weak acid. So this will make the solution basic. NaClO4, Na+, sodium ion, conjugate acid of NaOH, which is a strong base, so spectator, and ClO4-, perchloric acid, or perchlorate comes from perchloric acid, we discussed above, also a spectator. So this will actually be neutral, because neither one will change the pH of the solution. Neither one is going to create any more, produce any more hydroxide or hydronium ions from the water that's already there, so it's just going to stay neutral. Zinc nitrate, zinc 2+, highly charged, small, metal cation, acidic. And 2 moles of nitrate comes from nitric acid, which is a strong acid. So it is the conjugate base of a strong acid, which means it's a spectator. So overall, this will be acidic. Lithium chloride, lithium ion from lithium hydroxide, spectator, because it comes from a strong base. Chloride ion from HCl, spectator, and neutral. NaF, Na+, we've already discussed, spectator, F-, conjugate base of HF, so basic, because it is coming from a weak base, this will be basic. AlCl3, we've already done this entire example, so hopefully you remember this is acidic. And CaI2, Ca2+ comes from calcium hydroxide, strong base, so spectator. 2 moles of I- comes from HI, strong acid, also spectators. So this will be neutral. You should be able to identify if they're acidic, basic, or neutral. You should also be able to write out the reactions that are going to occur when these are splitting into solution. So when these actually dissolve in solution and split up the individual ions, and then from there you should be able to write the reaction showing how they do or don't react with water.